let's move forward then. Great. Okay, welcome everybody. Does my title make sense to anybody? Who gets my title? A few people, good. Okay, super. I guess, yeah, this is, I'm giving this talk because I like talking to people about my science. I guess it's also part of my review that we do every 5 years for after you get tenure or promoted to full professor. And so I'm taking this a slightly different direction. I'm not going to solve any great problems for you today. I'm not going to give you an exciting solution or a story about just exactly what happened in the past or how some system works. Instead, I'm going to talk to you about a perspective on how we do research in earth sciences, which I've been trying to kind of, is that right? Okay. Been trying to develop, and my group has been pushing forward and developing, I say, really across all fronts of what we've been doing. And so the title alludes to that. If you don't recognize it, I'm framing this talk in the context of Stanley Kubrick's 1964 Cold War film, Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. And so I apologize. Who's seen it? If you haven't seen it, that's your homework for the weekend, right? Go find it on Netflix. You can get it there and watch it. Great film. We'll be using it as a lead-in and an exit for this. But this is a film ultimately about the breakdown of command and control, right? Which is the failure to effectively and accurately kind of process information and make decisions, right, based on that information. And so hopefully that idea and that theme will kind of come through in this talk, because I'm going to be trying to talk about how I see that affecting our science in some ways I think that we can potentially get around that and improve what we do. So
make an analogy to Dr. Strange.
I am trying to drive too many things at once here. See if we can make this work. Okay. So let's start. This lecture is actually, this talk's going to start with some gossip. Okay. Several years ago, when we still went to AGU in person, I was at AGU. I was having a nice glass of red wine with a colleague who is a known gossip, and we were talking about we were talking about all kinds of stuff. And we were talking about a colleague came up, right? And this was an esteemed colleague, member of the National Academy of Science, a big dog, a gatekeeper, right? Not somebody from the University of Utah, somebody else. And when this came up, the guy I was having dinner with said, "Oh yeah, you came up in conversation with him, last month." And he said, "Oh, you mean the guy with the non-unique solutions?" And my initial response was to swoon and say, "Oh, they're talking about me behind my back. Cool." But then my other response was, "That doesn't sound so good. The guy with all the is that a diss? What is that?" Right? And so, we've got gatekeepers like this all over the place. This is General Buck Turgison. He's here in the war room with the president, and the information has to flow through him, right? And so when these guys are, aware of you and talking about you, you take notice and you think about it. And initially I was a little concerned about this, a little offended, but then I decided I was going to embrace it. Okay. And I thought about it, and I thought about, most of what we do leads to non-unique solutions. We're earth scientists, right? If we claim that we really know something absolutely, we should be checking ourselves, because that's seldom true, I think, certainly in the fields that I work in. And so my perspective on this, I think, kind of evolved, and I thought about, there are some things that my background is in paleoclimate science, right? And there are some things in that field which bug me. There's a lot of tendency out there to come up with a just so story, right? For whatever phenomenon we're studying, right? Whatever we're going out there to try to learn about. To come up with an explanation and a nice, neat, tidy story about how the world works. And there are good things about this, right? I maybe put it in a way that doesn't sound as good here, but this can be positive. It gets attention. It draws attention to the science. It gets people thinking about it when you provide a provocative and innovative explanation for something new. Certainly, it makes it easier to get your paper published in Science or Nature. That's great. And it gets attention again. So, but it's also true that these just so stories are almost always at least partly wrong. Okay. And I don't know, I published a Nature paper in 2004, which probably helped launch my career. I don't know. And looking back on that, we had a nice just so story, which is pretty conclusively at least like 85% wrong at this point. Okay. Doesn't mean it didn't move science forward, but this can have a detrimental effect too if it leads people in the wrong direction. And so bringing it back to the movie, here's Brigadier General Jack Ripper. And he's a pivotal figure in this movie because he draws a wrong conclusion. Right? He takes some very simple evidence that there's fluorine in our water supplies, and he processes that and comes up with a just so story that the communists are trying to poison us and poison our bodily fluids and take mind control of us, right? And in this case, it led to some pretty deleterious outcomes. All right, here's Major Kong jumping out of his B-52 bomber over a missile silo in Siberia, headed down on his nuke and starting a global conflagration, nuclear winter, nuclear devastation. So most of the outcomes in our science are not quite that bad, but I just was trying to find these analogies. So what do we need?
Resource for many of these analog studies will be an exciting place.
Lionel Mandrake here,
Cyber technology.
who
In summary, there are four main points.
who looks at that information, says there's multiple
for geologic studies of all types.
How far should we actually go with this?
These sedimentary units that are well
He managed to
exposed.
stop the war, but he got damn close.
Fascinating stories of the geologic history. Number
So
two,
my Lionel Mandrake is based
are telling us about how iron
And,
is actually moving the rock.
this is a general and very simple idea and approach to working with information, which I think we can use throughout our science.
Grand staircase as these steps.
So here's the equation in the form that we often see it. Basically, really just represents the philosophy and approach, taking new information and using it to inform our interpretation of evidence and our idea about how the world works. Okay. We've got two things here. We've got the model. This is what we're interested in. This is our just so story, right? This is our hypothesis about what's going on. And then we've got B, which is some new information, some data we collected. So Bayes' theorem breaks this down into a few pieces, right? So here's our interpretation. What we'd like to do is we'd like to assess, right, how likely our idea, our hypothesis, our model is given this cool new information we've got, the new data we've generated, the new observations we've made. Bayes' theorem says we can do that, and that the answer here is a function of three different things. The first is what we call our prior information, right? This is what we think we know going in. And people get really hung up on priors and Bayesian analysis and Bayesian thinking because they say, oh, wait, I've got to make a judgment, right? I actually would look at it a different way, think about it a different way. We're always making a judgment about the models, right? This is the probability that our model is true before we have any data. We're always making a judgment about our model when we do science. Just the very fact that we propose a certain hypothesis or model is a judgment call, okay? What Bayes' theorem forces you to do is to confront yourself with that, to assess it, to say, what do I actually know about this? How likely is this idea? And it may be that you have no reason to prefer one idea over another, or it may be that you've got good evidence or good information going in to support a particular model. So that's the first piece. Second piece is the new information that's brought in by our data, right, by our observations. And this is framed here as assessing the probability of the observations we've made given the model that we're considering. So if the model that I'm considering is right, how likely am I to find these observations that I've made? Are they consistent with that model or not? And then the final piece on the denominator here is kind of my favorite. Okay? This is the probability of the evidence itself. And this is something we really, pretty frequently ignore when we're doing our science. I've made some great new observations. I think they tell me something about the model that I have for the world, but we want to know how unique those observations are, how unique that evidence is. Is that something that I'm likely to find occurring in a large number of different scenarios, or is it something that's really unlikely and a really powerful constraint, really powerful observation? And so in Bayes' theorem, we have to bring that in. And it can be a difficult thing to assess, but it turns out to be a very powerful kind of way of weighting the information that we've gained. So let's talk about that probability of the evidence a little bit more. Right? It ultimately comes down to, are my new observations, my new evidence distinctive, or are they quotidian? Are they something that's just very commonplace? And so one more movie analogy here, just before we move on to hardcore science. Major Kong is in his B-52 and they receive a coded radio transmission. And he fastidiously, thoughtfully evaluates that evidence. And this leads to one of the best quotes that in the movie, I've been to one World Fair, a picnic, and a rodeo, and that's the stupidest thing I've ever heard, okay? So he's looked at that evidence, and he said, this is really weird. I would not expect to get this. There's no way I would get this unless this is a really serious situation. And this really is a unique piece of information, which I think should motivate me to accept a particular view of the world and move forward, right? And so, of course, he takes that coded information and he assesses it, he makes his decision, and that decision is we're going to go bomb the Soviets. And you saw what happened, okay? So in our science, here's some of our observations. Right, this is the information coming in, and we need to assess the probability that we would have a delta 18O value of minus 12.7, or this particular bed orientation, or this set of wiggles, right? And this gets pretty difficult, right? Because we're dealing with a very big system, a very large number of possible models or explanation for these. What are all the ways I can get a minus 12.7? Right? How unique and informative is minus 12.7? That's what we need to assess here. But ultimately, what this is nudging us toward is considering all the possibilities, right? So having multiple potential explanations for these observations and considering each one and saying which ones are consistent, which ones aren't, but also how many different ways can I get these observations? In which case, I need to keep multiple models in mind. And so in a practical sense, we can do this in kind of one of two ways in these real world problems. It's possible, or if it's possible that we can do this, we could potentially go out there and test every possible hypothesis that we could come up with. What are all the potential explanations, all the models? And we could assess each one. And then having done that, we can assess how likely the evidence is because we've looked at all possible solutions. In many cases, that's impractical. And so what we end up doing is taking a numerical shortcut. And we try to assess some representative set of models, okay? Using an algorithm which searches lots of different potential hypotheses and gives us a posterior collection of possible solutions, right? That's sampled from the whole family of potential models. And there's lots of good software out there that actually makes this not too hard for somebody, who isn't super astute at this stuff to get in trouble or to design and do science with it. Okay, so that's the lead in. And what I'd like to do in the rest of the talk today is really just walk you through three areas of our research, pretty different areas of our research where we've been applying this. And I'll do it with a little bit of a historical kind of framework to how I came about this too. So we're going to start with migration. migration of animals. And this is something that, although my background is paleoclimate, I got involved in this fairly early on in my career through interactions with colleagues who are doing this work, using stable isotopes to try to trace the movement of animals as they went on seasonal migrations or short-term migrations or historic migrations due to climate change, things like that. So a couple of characters here I'll try to show people along the way. Mike Wonder, Brian Norris. These are a couple of the scientists who've been working particularly on long distance migration of birds and got me interested in this. And these are animals that often have impressive, long distance migrations, hundreds, thousands of kilometers, little critters, right? And they're hard to track, right? It's really ineffective to try to trace them by sticking tags on them. Many of them are too small for traditional GPS tracking techniques and things like that. So what researchers recognized starting in the 90s was that these things are carrying geographic information in their tissues. The isotope values of, for example, the feathers of this American redstart up here are grown at one end of its migration range. Those feathers are grown there. They lock in an isotopic signature from the local environment. And we can potentially use that. We can capture them at the other end of the range as evidence about where they might have been. And Mike Wonder down here in particular was very instrumental in this field in developing a Bayesian approach to doing this work. And it starts with the idea that our model here is that the individual came from somewhere on a map. We maybe can draw a box on a map or define a region where they might have come from. And then we can divide that region up. And if we can predict at each place on that map what isotope values we would expect to find, what the distribution of values we would expect to find at that location would be, we can compare that with our feathers using Bayes' theorem, as we've seen before, and generate information on where that individual might have come from. So our model is a geographic model. Each hypothesis that we're going to evaluate is a grid cell on a map. And we're going to be evaluating the hypothesis, the model, that that is the true origin of this individual. The likelihood function, that how likely is the evidence given our model, we can evaluate if we can estimate a probability distribution for the isotope values of feathers grown at that site in that grid cell, right? And then because we have a constrained problem, let's say for this particular species, we know that it breeds within this set of polygons, we can actually evaluate every single model, right, on this map. We can evaluate all of the different grid cells on this map, and therefore we can fully kind of solve the Bayes' theorem equation and come up with a probability for each of our models, okay? And so we end up with is a probability that each grid cell is the location of origin, and we can integrate or sum those in different ways. And so here in this American redstart example, what we've done is we've got individuals that are captured on the wintering range down here around the Caribbean. This is the breeding range. We've divided it up into several different kind of subregions. And these bar plots here basically show the cumulative probability that individuals captured wintering here would have bred in this polygon or so on and so forth, right? So just from capturing these guys, measuring their feathers and applying this kind of information approach, we can start to elucidate patterns here. What this shows is a very nice example of what we call chain migration, where there's connectivity between different parts of the range. The folks over here tend to migrate down here. The folks over here tend to migrate down here, right? And so this is not a random pattern. It's a structured pattern. And this information can be taken and used, for example, in conservation work then, right? So knowing that if we have habitat destruction, in one part of the wintering range or the breeding range, that we would expect it to affect a certain subset of the population. So a lot of our subsequent work on this migration stuff is actually focused on trying to develop tools that make it possible to do this type of work for a range of different species, range of different types of organisms, ranging from butterflies to humans. And so I'm going to focus on our ability to solve this part of the equation, right? To estimate the probability of a particular set or a particular isotope value in tissues, given a particular location on a map, right? What would we expect the distribution of values in tissues, body tissues to be at a given place on the map? And so to do this, we need a few different things. One is if we're going to take this approach where we evaluate this at all the different possible locations of origin, we need to be able to make these predictions every place. And so we do that through spatial models or isoscapes, right? And those are built on data. And so one of our efforts has really been focused on developing databases where the vast swath of people that are out there generating isotope data from the environment and from animals can compile and share their data so they can be used to develop these geospatial data products. And so we've got a couple of databases, one focused on water, hosted out of CHPC here, and another one that's hosted at Texas, the TAC Center there, which is a broader kind of community-wide ecology-focused isotope database. This is former grad student Annie Putman, who was a big force behind the WIBB and getting it set up and going here, and that work continues. The next thing we need once we have all this data is we need models, and we need the ability to generate these spatial models from those data. So we've done a lot of this in-house, and we work on different approaches to this. But another thing that we developed actually late in the time that I was at Purdue and have continued to develop through other projects is this online platform, web-based platform called ISOMap, right? Which basically is a web interface that's set up to allow people to kind of work through the process of taking the data and turning them into these map data products. So here's hydrogen isotopes and precipitation across part of Europe, right? Modeled from these point data and a geostatistical model in this case, right? That gives us now predictions at each place where we might want to go and assess the origin potential that our individual that we're working with originated there. And so that's water isotope data, but ultimately we're interested in animals and organisms. And so we also need to understand how the organism samples the isotopic signature from the environment. And this was a major focus for Sarah Magosi, who was a postdoc here with us for several years. And she did a series of projects looking at this. But this is a really neat one that was just published last year, where she was combining agent-based models. This happens to be Red Butte Creek, Red Butte Canyon up here. Combining agent-based models. So we're taking individual birds and simulating their movement and their foraging behavior in the habitat. We were also modeling isotopic variability within food and water in this habitat, across this habitat. We're basically looking at how individuals, as a function of their behavior and physiology and the environmental variability, would integrate the isotopic signatures from that habitat into their tissues. And there's a long kind of background for doing this kind of work and good reason for doing it, but ultimately what we're interested in is understanding how individuals sample their environment. And I won't go through this, but basically she showed that kind of with the full-blown model, we can really nicely reproduce the variability and the patterns that we see when we go out and we sample individual birds that have been living and molting, growing feathers in Red Butte. And so the final component of this then is once we've got all these pieces of information, there are lots of different people who want to be able to do this. I should stay back here so the microphone's in front of me. Ranging from hardcore scientists to amateur hobbyists who happen to be interested in a particular type of critter to managers, right? And so we would like to be able to kind of enable the community to have access to and do these kinds of analyses in a range of different ways. And so kind of the last component of what we've been developing in terms of resources to support this type of work is a set of software, open source software, which supports kind of the end-to-end analyses. We take our data in at one end, we take our isoscapes in, and we can do flowcharts are not interesting when anyway, here they are. You can work through a variety of different workflows to basically come up with answers, right? If I want to test a hypothesis about, or a set of hypotheses about this organism having come from this state or this nature preserve or outside of that nature preserve, the tools in here allow you to kind of work through that, right, and get some answers out the other end. So Chao Ma, another former postdoc, was instrumental in kind of getting this launched. And it's now an R package called Assigner, which is out there for you on CRAN or GitHub if you want to use it. Okay, so that's the animal stuff. Let's talk a little bit about water now. So, again, with the animal migration stuff, I'm not a migration ecologist, right? I don't have a particular critter that I love and want to chase around and really, really passionately want to know where it came from. I'm more interested in the tools and the approaches and trying to support those, as you can see, and develop them further. Water is something that we actually work on a lot in my group. And so this is really where it started to kind of come into the group, and these approaches and this way of thinking kind of, began to be a currency in how we did our work. And this really starts with Yusuf Jamil, a former PhD student. Yusuf did a series of projects while he was here as a PhD student, looking at municipal water here in the Salt Lake Valley, so public supply of water. And in this particular project, he was working with folks at the Jordan Valley Water Conservation District, one of the two major water wholesalers here in the Salt Lake Valley, and getting samples from throughout their distribution networks, as well as the wells and the reservoirs that they were drawing water from. And the ultimate question was, could we use the isotopic information to help inform our understanding of how water moves through their distribution system, where it comes from? Okay. In this case, water is something that can mix, unlike bird feathers. And so we have water coming into the system from multiple points, multiple directions. We have the potential that at any given point in the distribution system, we may have water, not necessarily have to, but we may have water that has come from a few different places. And so the models we are considering here are mixing models, where we've got different sources. And we're considering, when we sample at one place, our hypotheses or our models are, what are the possible mixtures that could have contributed to and given us that sample? Isotopes are our evidence again. And in this case, we're lucky in that many of the water sources used here in the Salt Lake Valley have different isotopic compositions, which gives us the power to potentially use this. This is no longer a problem that we can really discretize in the way that we did the bird problem. And so in this case, we're going to use Markov chain Monte Carlo analysis to do that process of searching the model space, right? Trying to evaluate kind of representative sets of potential mixtures, potential combinations of sources, and come up with a posterior distribution that is a sample of the mixtures that work given our data. Okay. And the other thing that we're going to add here is we're actually going to bring in information in our prior part of our Bayes theorem equation. Okay, so we're actually going to take something that we know beforehand and use that to inform our kind of prior understanding or estimate of the probability of our different models, the different potential mixtures. So for this prior probability specification, again, this is something people get hung up on, and with good reason, because we have to make some judgment calls here. And so we have to think about what's reasonable, what do we know, what constraints do we actually have? So in this case, Yusuf based this on two pieces of information. One is the assumption that we had production information from the different sources, right? Most of the water comes from the Jordan River or Provo River, Jordanelle system, right? And so we upweighted the probability of that being the source to any particular place on here, just because we know that it's producing a whole lot more water than all the other sources. And then we also used a simple metric of distance, right, between, for example, any source. So here's a water treatment plant that takes water from the Jordanelle system, Jordanelle Provo system. And so we can look at these are our sampling points. We can look at the distance between them, and our, starting idea here was that the probability that that's an important source decreases the further we go from it. That makes sense. So one thing you can do with priors, though, I mean, they're very powerful and useful, but you want to make sure that your answer isn't totally dependent on them. So I'm actually showing both here. And so you can see, for example, for this Jordan Valley water treatment plant here, which actually supplies 80% of the water to the system at this particular point in time. You can see that our priors are pretty high. So the color coding's over there, but our prior estimate is that this is a super important source here, and maybe it dies off a little bit as we get further away. Whereas this well here, which produces very little, we estimate a somewhat high probability locally, and then not really much anywhere else. Okay. So then we add the isotope information, right? We do the MC-MC analysis, and we look at our posterior probabilities the same way, our mixtures. And so one thing that's encouraging here is we see that the pattern here is not just the pattern that we put in at the outset. That means that our isotopes are bringing in some useful information. And it's also information that makes sense. And it's kind of cool. We can see various pockets, right, of the supply system here, the distribution system, where we have connections to this plant. But even though they're very far away, this is inferred to be the dominant source after we add the isotope information. If we look at this little well over here, we can see, yes, we already predicted at the outset that this is where we would see its water if it was important. But now with the isotopic information, we can actually see there's parts of the supply, the distribution system there that look like they're dominated by that well water. Okay. So we've added a significant amount of information from this. And we can go and we can do this and analyze it in different ways, and it becomes potentially a tool that can be brought into management. It can be brought into responses to problems with the system. And Yusuf worked with the folks at the Water Management Agency there to kind of work through a series of applied problems that they had and were interested in. Okay, let's look at a similar kind of thing with lakes. I put my picture up there nice and big because I don't actually get to do much first author lead work anymore. And so I'm going to take proud ownership of this one, something I actually got to do and figure out myself. Largely really just leveraging what I learned from Yusuf. But we're going to do a similar problem here, similar approach, but look at water in lakes. Where does it come from? And more specifically, when does it come from? And this was building on work from actually some paleoclimatologists who'd studied isotope compositions of lakes throughout the US and had made the argument that the lake water was kind of an unbiased integrator of precipitation. Right? If we were in a climate where there was twice as much winter precipitation as summer precipitation, they argued you could go to that lake and you would expect to find a mixture of 2-to-1 winter to summer precipitation in the lake water, which would make it then very useful as a potentially a source of paleoclimate information. We wanted to revisit that using the isotopes. This is another mixing problem. We're going to have winter and summer precipitation as our two sources, two end members. And most places on Earth, winter precipitation is isotopically light and summer is isotopically heavy. So we've got a nice signal to work with. A problem with lakes is that they sit out there in the open, unlike those pipes, and they lose water to evaporation. And when that happens, the isotopes are affected. And so we needed a somewhat more sophisticated or more complicated model for interpreting these data and drawing inference from them than we needed for the Jordan Valley one. So in this paper, we just kind of built this up. It starts, and it's a hierarchical model. So one of the nice things about this kind of work is we can break our problem down into pieces. And if we can develop a mathematical representation of each of the steps, we can use that, right, in our evaluation of the probability of our data, right, given the particular model. So our model starts with this: winter precipitation, summer precipitation, and some mixture, right? And that gives us a source or a value for the lake before evaporation happens. But then we also have potential for some evaporation. And fortunately for us, that evaporation has an isotopic effect that kind of moves us in a different direction in hydrogen and oxygen isotope space. And so it's distinct from the mixing process. It has a distinct effect, and we can model that. And then we get a value out here, which is the true value of the lake water. And then the top level of our hierarchy is always our data model. How do we sample that? And so we've gone out there and got a sample of that lake, and we measured it on a mass spectrometer or a laser instrument. And so we don't actually know the exact value for that lake, right, the idealized true value, but we've got some estimate of it, and we can represent that as uncertainty. And so we're going to use MCMC again to solve this, and each model that we're going to consider starts with some estimate of the source values, some estimate of the mixture, some estimate of the evaporation process, and some estimate of how our measurement samples the lake value. Okay, we can integrate this, across a huge range of different possibilities, again, using a desktop computer. And so these are some of the results here. And just to summarize, this is showing us the seasonal bias relative to what we would expect, an unbiased mixture of precipitation from the two seasons. And what it's showing us is that there's huge swaths of the country where lakes are winter biased. Basically, anywhere we have snow, we have more winter water in the lakes than we would expect, right? However, there's also parts of the country, particularly out here in the Great Plains, where we have a decent number of lakes that have more summer water than we would expect. So are lakes unbiased integrators? Well, a lot of them are pretty close, right? And so that's encouraging, but it also looks like there are kind of systematic deviations from that, where we have situations leading to both winter and summer bias in the filling of those lakes. Okay. So the last set of applications I want to talk about comes back to my original passion, right? Paleoclimate reconstruction. You guys are looking at tree rings and trying to figure out what the climate was like in the past. And this is a super tricky one, right? And it's an exciting field. We get to look back into the past and try to understand how Earth systems worked under crazy ranges of different extreme conditions. Lots of opportunity for learning, a huge amount of opportunity for just so stories. Okay, but it's inevitably a science which is really fuzzy, right? We're trying to look deep into the past and understand how a complex system, climate system works with very, very imperfect evidence. And so I actually think that out of all these applications, this approach is potentially most powerful and best suited to this set of problems. We've got lots of different ways of reconstructing climate. They're all imprecise and poor. Any proxy that we measure maybe tells us something about the climate variables we're interested in, but there's lots of other things that can complicate that signal. And because we have lots of different types of approaches, lots of different proxies, it's really powerful potentially if you can put those together, right, and leverage their complementarity. One of the fundamental problems, as I see it, though, is that this field for decades, century, I don't know, has been working this way, right? We go out, we generate some data that we're interested in pursuit of reconstructing some environmental variable. We want to know what temperature was, okay? Almost inevitably, we want to know what temperature was. So we're going to go out, we're going to generate some data, and maybe we've got some equations that, we fit to some experimental data telling us how those data change as a function of, the temperature. And we're going to just plug and chug through this equation, and we're going to get a temperature. And we get an answer, we get a temperature, right? Because that's how we set it up. But that's not how the world works, right? In reality, we have something up here that we can measure. And we've got a big, complicated climate system, environmental system down here, which is filtered through some set of processes that then gives us this thing that we can measure. And so in this Bayesian approach, what we need is this model. We need the forward model. We need to start with the environment and go forward to produce the data so that we can say for a given model, a given hypothesis about what the environment looked like, how likely are the data that I've gathered, the proxy data that I've gathered and the observations I made. So this starts with building this approach, this kind of forward modeling approach to representing proxy systems. And inevitably, it forces us to think about more than just temperature, right? We have to think about all the other things that are affecting the critter or the geochemical system, whatever it is that we're studying. So I got to do a sabbatical a few years ago. That was awesome. Thank you, Brenda. Thank you, G&G. And again, this is one of these rare cases where I got to get away and lock myself up with some smart people and a computer and do something new. And so I took this work that we've been doing with water, and I started to try to build it out into something we could do with paleoclimate. And so looking a little more complicated here, but this is just a hierarchical model like we talked about before. The first layer is a model for the environment. And in this case, we're using a time series model to actually simulate how temperature, say, changes over time. So this is one iteration of this model simulating temperature change, ocean bottom water temperature change over some period of time, okay? And then we've got a proxy system model, which says, how do the things that I can measure reflect these environmental conditions? So here's our simulated time series from our environmental model. And then we've got layers in an ocean core where we've measured proxy data. So we can take the conditions we've simulated in our model. We can predict not a single value, but a distribution of values we might expect given the conditions we've simulated. And then we can compare them to the red point, which we've actually measured. Okay. And that becomes the way that we then evaluate the likelihood function, the probability of these of these data points, the evidence, given this model for the climate. We do this millions of times, and we generate a set of models that's consistent with the data set that we have. And this gives us kind of a different way of looking at the information. And so this is a longer view of that same record that we zoomed in on before. And the blue is kind of our traditional way that we would interpret these data, where we treat each data point as some independent, stake in the mud that tells us what the climate was at this point in time. And then what we see in background here, is thousands of simulations of models from our posterior about what might actually been happening. Temperature and isotope composition of seawater down here. Okay? And so you can see that they're a little bit different, right? We have a smoothing here, which is inherent to the fact that we're using this time series model. And we don't think that climate jumps back and forth discretely between the points we happen to have sampled within the core, right? That there's noise in there. That variability is, in some cases, potentially a true signal, but in most cases, it's probably noise with proxy. And so, the model kind of takes that into account and tries to explain all of the data at once, right, with a unifying kind of set of information or a unifying model, set of models. And so there's a lot of advantages. Just to highlight a few things that we get out of this. One is that we get a propagation of uncertainty through all parts of the model and throughout the time scale. So we can see, for example, parts of the record here where we have relatively few samples, right? And our envelope of uncertainty gets wider because we just have less information constraining that piece of the record. But we can estimate uncertainty, between our individual data points because our environmental model is kind of reflecting how information is propagated from a point we sampled to a point we haven't. Another thing that's nice about this is if we use these time series models, we can make predictions continuously, essentially, throughout this record, and then we can compare them to whatever observations we have. So these are two different sets of proxies. Don't worry about what's what, but you can see that they're not sampled at the same levels in this core necessarily, right? That doesn't matter because anytime we have an observation, we can evaluate its likelihood given the model that we're considering. And we can use that information as a constraint on our system. And another nice thing is we can integrate many different proxies that are linked together to common sets of environmental conditions. And we can develop a covariant representation of the possibilities, right? So we're representing the whole system at once. And that means that our bottom water temperature is not independent of the seawater temperature in any given model, right? There's a relationship that we're exploring and finding within these data. And so, for example, if we take these and flip them on end, we're now looking at changes in bottom water temperature and seawater oxygen isotope values over this time series from old to young. We can actually look at the density here and we can see that during this period of time, it looks like Earth's climate shifted between three semi-stable states. We've got a relatively warm state here with relatively low isotope values in the ocean water. And then we shift to a somewhat higher isotope value state here with similar temperatures. And then we descend into the Pliocene, glacial cycles here, where we're in this space, right? And so we can start to kind of see how these multiple parameters operate together, and at least given this one record, kind of how we are moving through climate space, multidimensional climate space over time. I'm going to skip that one. That's hypothesis testing. Okay, and so just to, a couple of things that are going on now. I'd like to highlight this project here, Cecilia Benavente and Randy Ermis, where we're looking at Triassic climate. And in this case, we're even further back in the past. The data are even worse, right? We don't have ocean cores to work with. So we're trying to integrate disparate proxy records to types of proxies to understand what climate patterns looked like at various points in the Triassic. We've got a variety of proxies to work with. And in this case, instead of using a time series model, because we don't have dense information in time, we're actually looking at different climate states, different chunks of the record, and trying to look, our model in this case is a model of meridional temperature gradients. So equator to pole temperature gradients, and trying to fit those or constrain those with the data. And so here's some very preliminary results from that as we go from the middle Triassic in red to the late Triassic, and then this is the modern for reference. What we can see, Triassic was hot. We knew that already, right? And but what we see is between the middle Triassic and the early late Triassic, what seems to be a substantial shift in the nature of the meridional temperature gradient. Middle Triassic was quite steep, and it looks like this is probably maybe exaggerated. We don't have a lot of high latitude data here, but in the late Triassic, we see what evidence for a much flatter gradient. Okay. We haven't integrated every piece of proxy data in this, and there's actually some independent data which is somewhat consistent with this. We get into late Triassic, we see evidence for humidity on land masses throughout Pangea basically, whereas in the middle Triassic the equatorial regions were quite humid and not the poles. But anyway, it's a way, again, it's an attempt at trying to integrate these different proxies within a common framework and bring new information in. And so then the final thing I'd just like to talk about for a minute is CO2, which we all know and care about today. And we would like to know more about in the past. And so over the last 3 or 4 years, I've been involved in an NSF research coordination network led by Beryl Honish at Vermont, where we've been trying to go in and compile all the different proxy data that tells us something about CO2 over the Cenozoic. And here we got even more, we got a whole, people love CO2, there's a whole portfolio of proxies. Turi Serling's got his own proxy, which everybody knows and loves him for. This one, and then there's all these other ones, right, too. And this is the Cenozoic, right? This is not that far back in time for geologists. The data are all over the place. And we've known this for a long time, right? If you take an individual proxy, you try to reconstruct CO2, you can find parts of the record where you get some similarities, but this is a mess, right? And this is after we've gone in and done a careful job of trying to ensure consistency and bring these into a common database. So what do we do with this? Well, usually one of two things. One, I like this proxy. I'm going to throw away the rest of the data, put my stake in this proxy, and draw a line through it. That's the truth, okay? Or the other thing is, good God, what do we do? Let's just squint and, maybe there's some changes here, okay? We think we can do better, right? We think we can use this approach, and if we can develop proxy system models for at least the best of these, the ones that we have the most data from, ultimately, most broadly useful, we can start to combine these in a way that's much more methodical and systematic and quantitative. And there are problems in the proxy development side that have to be dealt with too. We don't know exactly how some of these work, but I think there's a lot of ground that can be gained on the statistics and data interpretation side from this Bayesian approach, as well as simultaneously moving forward to better understand the proxy systems themselves. And so I'm part of a NSF FRES proposal that just got supported this summer, led by Isabel Montanez at UC Davis. And the Cenozoic wasn't enough of a challenge for us. So in this project, we're going to do the whole Phanerozoic. we've got a huge range of climate signal to work with, and our CO2 proxies, once we get back into this part of the record, let me just say they don't look any better than what we saw in the Cenozoic. So stay tuned for this. There's components of this that involve compiling data, trying to standardize data, generate new analyses that give us better constraints on our data interpretation. And then our group here at Utah, with a new postdoc that'll be starting hopefully this winter, is going to build these proxy system models and do a variety of different types of Bayesian inversions to try to reconstruct the record. Okay. And I'll just say before I go on to the last slide that this is something that we're doing. I've provided some examples here, but it's again a theme that's kind of pervasive throughout the group right now. Brendan Fisher-Femmel, who just is finishing up his PhD, was applying this approach to interpreting pedogenic carbonate data in a paleoclimate context. Deming Yang, who's sitting back there, has been looking at leaf lipid biomarkers and reconstructing paleovegetation using this approach, as well as potentially animal movement, using movement models and combining them with time series data from growing tissues like hair. And Paige Austin, who's a PhD student right now, is trying to develop a similar approach that will help us use isotope data to partition evaporation and transpiration fluxes from ecosystems. So there's a lot that can be done. So, my music playing? Oh, I knew it wasn't going to work. Well, you'll have to go watch the movie. The closing song really brings tears to your eyes. We're back here in the war room. We're all on our phones. We've got our own favorite contact on the other end, our proxy or our measurement or whatever that's bringing in information. Our challenge is to figure out how to parse that, how to interpret it, how to bring it together in a way that we can make the best decisions that we can and keep our options open, right? Make sure that we keep in mind the multiple possibilities that might exist when we're trying to interpret the world. And don't do anything dumb, okay? I think this is a great way to approach that problem. And there's lots of things we're doing with it, but there's a lot more. So anyway, let's go have a beer at some point or a cup of coffee and talk over what we could do. Thank you.
Well, thank you, Gabe. We have time for questions. I think we'll do the same as we did last week. We'll first take any questions from the in-person audience. And then if you're on Zoom and you have a question, just please raise your hand in the chat and I'll try to monitor that and we'll get to those questions. So anybody in the audience?
Oh, that's a good idea. Yeah, let's see what we can do here. No.
Perhaps just stop sharing.
Try again.
Gallery. There you go. Gallery.
Okay, good.
I have a question, Gabe.
Yeah.
If 5 years from now.
And really try to speak up so we can catch it on the mic.
5 years from now.
5 years from now, you and I are having a slice of pizza and you are saying, boy, gee whiz, this worked so well. I'm so impressed that we discovered X about the Phanerozoic or about the Mesozoic. What is at stake there? What is that thing you're excited to have discovered?
Yeah. Right. So what is the thing we'd be excited to have discovered? You want the paleoclimate answer in particular? Or
I don't care.
you don't
Tell
care?
me. You're the one telling me.
Yeah, okay. Well, I mean, I think one of the big outstanding questions really is having a better understanding of the range of feedbacks, right, in the carbon cycle. And so with the CO2 project, I think one of the things we really would like to do is get a better handle on through events, both multi-million year long events as well as short ones. What's the size of the change in a quantitative way, because that can help us start to drill down into the feedbacks. And so, I mean, organic carbon and soils and vegetation is a big one that I'm interested in. And so I think one of the hopes here is that we can actually, one of the types of models we'd like to use is actually a a physically based model, right? A process-based model. So we can start to evaluate not just what's the pattern, but also what might the drivers be. And so I'm hoping we can zoom in a little bit better on our understanding of how active the terrestrial carbon cycle, soils and plants actually are in modulating and contributing to climate change over geologic time.
So like you might say, whoa, we figured out why the pedogenetic answers are always much higher than the other.
Well, that would be more kind of like a, what are the proxies? How do we use the proxies kind of result, which would be cool and important too.
From an environment to data,
Yeah,
that sort of forward model.
yeah,
That's
yeah,
the
yeah.
kind of thing you'd like to figure out.
I would like to figure that out, but no, I would like to understand how much carbon storage in soils changes throughout the Cenozoic, right? Or throughout the, has it been fairly constant, or, you know, some models suggest we've had a factor of 2 or 3 changes, and that could be big for the atmosphere, right? And so how does that change? How stable has it been? How static has it been? How dynamic has it been? And over what kinds of timescales? Nick, let's go to Nick.
So with like, some of the forward-based modeling for going how should that color our data, but also just in terms of the sort of time series fitting, that seems really, really heavily colored by modern systems and how those behave. As you go deeper and deeper and deeper and deeper into like late, early Paleozoic and stuff, you're increasingly going to encounter non-analog systems. Is there a typical way you account for that, or do you just know that like when you hit those non-analog system behaviors, you're gonna see things that are sort of way off skewed from how your model is going to predict their behavior?
Yeah.
Can you kind of repeat
Repeat
that
it.
for the?
Yeah, so the question is really the ultimate question in, I guess, deep time research, but, you know, research on the geological past in general, which is further back we go, the less we know about how things work. And so we have to apply assumptions or knowledge from the modern to interpret the data from the past. And that's increasingly risky as we go back. So yeah, I guess I have 2 answers. One is that's inevitable, and we just have to keep it in mind. The other is to the degree that we can break things down to fundamentals of physics, chemistry, and biology, we're on better ground in that respect, because we think a lot of those rules don't change. You know, things can change, but so that's one of the reasons why I really digging into the systematics of our proxies and trying to develop formal models to explain them. We can't always go back to the physical principles, right? The first order principles, but I think the closer we can get, you know, the better footing we're on for extending our interpretations back in time. Yeah.
Is there a capacity to load or even unload the probability prior? Allow more room for your basic model to move and potentially account for how those non-analog like
Yeah.
essentially have the sort of purely modern informed versus this more loosely
Yep.
allowed to play around.
Yeah, so there's all kinds of possibilities. You can use even different model forms in the same inversion, right? So if you don't know how something works, you can put in a model that has flexibility to represent multiple possibilities. You could have priors which change over time to reflect your confidence in how much you think you know about how this thing works, how this process works. So there's a lot of things you can do to try to more honestly represent your knowledge or lack thereof. Benji?
So, for the 3 first application you mentioned, like bird migration and water mixture in the tide and mixture in the lake. It seems like what you're saying is basically the observation kind of is consistent from what you expected in a way. I'm just curious, like anything like surprising or anything like kind of unexpected that's kind of different from what you kind of predicted before you make that observation?
Yeah, well, I mean, just to take the lake example as one, right? In that case, you know, the expectation and our prior going in was that the lakes were an unbiased recorder of precipitation. Now, there's reasons you might think hydrologically that they would prefer, they would be skewed toward one season or the other, but the dogma that we were, testing or trying to evaluate there was that they're unbiased integrators. And what we found in the data was that they weren't, right? So once we added the isotopic information in there, we found strong evidence that at least like 25% of the lakes that we looked at in that nationwide data set were strongly skewed toward winter or summer. Right?
So what's the kind of missing in previous understanding?
Yeah, so the previous understanding was really just kind of a phenomenological one based on previous looks, primarily at isotope data. So yeah, then the question is, what do we add to our model to make our prior more closely aligned with what we think is really going on? And I think in that case, it's most likely differences in runoff efficiency for different seasons. So in places where we have a snowpack, a greater fraction of that water gets released rapidly and becomes runoff, groundwater maybe, and then runoff, but ultimately ends up going out into streams. And in the summertime, more of it goes back to the atmosphere, right? In those Great Plains examples where we saw summer bias, those are a little harder to explain, but I think probably, that's an area where we have intense summer precipitation and convective storms. My guess, my hunch is that that bias we're seeing there is driven by the fact that those intense storms, a greater fraction becomes runoff instead of infiltrating or evaporating also. So, yeah, I think in all of those cases, there were multiple ideas going in, and the isotope data were helpful in constraining which hypotheses, which models were right.
I have some more questions on that, but I think I'm going to turn to the Zoom. Maybe I'll ask them afterwards. Is there anyone in our Zoom audience that has a question? At the moment, I'm not seeing any hands raised. If not, I'll ask my question. In that same lake, to what extent is this bias simply explained by the seasonality of the amount of precipitation?
That was actually taken into account in the null model prior. So what I was showing you was bias relative to that.
Okay.
So how much overweighted was winter precipitation relative to its contribution to the total annual precipitation?
So it's all weighted, to begin with.
Yeah.
Okay. Well, actually, we're past time, and I don't see any other hands raised on the chat. Hopefully, I'm not missing something here.
I think those are earlier.
Old, I think.
Okay.
Whoops.
Yeah.
Cool. Well, thank you everybody for coming out, whether in person or on Zoom, and I hope we can all get together at some point and do this in this room sometime before I retire.
Thank you. Join me, Jen. Thank you, Jen.